Welcome to Lecture 10. We will see how well this goes in the middle, well, not in the middle of, but towards the end of a big thunderstorm. You may still hear the thunder rumbling around. It should be close to the end here. Anyway, we are talking now about Chapter 3, which gets us into formulas for calculating derivatives. And particularly today, we're going to look at shortcuts for calculating derivatives of two kinds of functions, polynomial functions and exponential functions. So let's take a look at, we'll build our way up to polynomials by starting with the easiest ones. Suppose that you have a constant. So what we're talking about is a function y, which is a constant. So the graph of it would look like what you'd expect, a line right there. Okay. Well, the tangent line to that line would be horizontal, and so the derivative should be 0. So in fact, if you take this as your function, f of x, and then take the derivative, and say the derivative is, by definition, the limit as h goes to 0 of f of x plus h minus f of x all over h, then you ask yourself, what does f do to x plus h? Well, what does f do to anything? F is a constant, so the answer for f of x plus h is c. And what's f of x? Well, same thing, c. So you get c minus c over h, which is 0 over h, and of course 0 over h is 0. So the limit of 0 is 0. So the derivative of a constant is 0, as we already knew. So from now on, we don't have to use this anymore, because we just know the derivative of a constant is 0. Similarly, what if our function is a line, y equals mx plus b? So this is our f of x now, new function. So once again, we could write f prime at x, and write this as the limit as h goes to 0 of f of x plus h. Well, I'm just going to write out what f of x plus h is. It's m times x plus h minus, or plus b. This part is f of x plus h. You replace x in the argument of the function by x plus h. So that's f of x. And then, I'm sorry, f of x plus h. Now we have to subtract f of x, which is mx plus b. And then divide that whole thing by h. So when we do that, we get the limit as h goes to 0 of, now we multiply this out and you get mx, I'll go ahead and do it, mx plus mh plus b minus mx minus b all over h. And as you would expect, the mx is going to cancel, the b is going to cancel, and it's just leaving you mh divided by h, which reduces to m, and this limit as h goes to 0 of m is just m. So if you have a line of slope m, whatever m is, the tangent line to a line would be the line itself, and so the slope of the tangent would be m. So we have just shown that the derivative of something like mx plus b is m. The derivative of a line is just the slope of the line, to no one's surprise, I hope. All right, well, if you go to x squared for your function, we've done this one before, but maybe not in complete generality. So what would the derivative be for x squared? Well, it's the limit as h goes to 0 of f of x plus h. Well, we replace x by x plus h in the squaring function. So it's that minus f of x, which is x squared, and all of that is divided by h. We can multiply out the x plus h squared, getting x squared plus 2xh plus h squared. And then you got to subtract x squared. And then you divide that all by h. Of course, x squared cancels. And then you get to factor out an h. And so that leaves you with h times 2x plus h, all divided by h. H cancels, and as h goes to 0, 2x stays 2x, h goes to 0, so you're just left with 2x. So the derivative as a function of x squared is 2x. Now we can play this game all day, go to x cubed and ask what is the derivative of x cubed and do the same kind of thing, multiply it all out, and in the end we would end up with, as many of you know, 3x squared. So if f of x is x cubed, f prime of x would be 3x squared, which you could get by cranking through all of this. And then you could go to x to the fourth and find that the derivative for x to the fourth, the derivative would be 4x to the third. If you've not had calculus before, you can still probably see the pattern here. If you go all the way up to x to the n, you'll eventually get n times x to the n minus 1. So this is what the book calls the power rule, and I call the high school rule, because this is the only thing that high school students remember, that if f of x is x to the n, then f prime of x, the derivative, will be n times x to the n minus 1. Now, I can prove this for you, by going through all of these, and you get the picture, and it's believable when n is an integer. But actually, it's true even if n is any real constant. This is going to be very, very important for you to keep in mind. It's got to be a constant that we're talking about. So, for example, if we're talking about x to the pi power, then what is the derivative? By the way, I'm getting tired of writing f of x equals blah, 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 and then f prime of x equals. I'm going to use the Leibniz notation. Remember the Leibniz notation talks about dy dx, or d anything. If we're talking about salary, ds as a function of time, this would be the change in salary with respect to time. We label our letters anything that you want. Well, this notation also has one other very nice advantage. We can think of it this way. We can pull away the d over dt and think of this as, get ready for a fancy expression, this is a differential operator. It's something that operates on a function. In particular, this time it's the function s, it's the salary function, as a function of time. So you can think of d over dt as the derivative with respect to time of whatever's in the parentheses. So I will often write this. So please make sure that you understand what I'm writing here, the derivative with respect to t of. So if I write here in front of x to the pi, d over dx, read this in English now, this means the derivative with respect to x of whatever in the parentheses. Now I see a lot of people writing, I've had a lot of experience with this. If they want to take the derivative of x cubed, they'll write dy dx x cubed. And you see this is wrong, because what this means is take the derivative of y with respect to x and multiply that by x cubed. That's not what they mean. What they really mean is the derivative with respect to x of x cubed, which we already know is going to be 3x squared from up here. But this operator applied to a function is an easy way of saying take the derivative with respect to x of. So one other thing while I'm talking about this differential operator, if you just write d over dx and read this in English, it says the derivative with respect to x of. And you see that's missing something. There's got to be something that you're taking the derivative of. So it's a prepositional phrase without an object. What's the object? What is it that you're going to take the derivative of here? Okay, so what I want to say is that if I take the derivative of x to any real constant, and it doesn't matter what that is, then the derivative with respect to x of x to the whatever constant it is will be, well, here's the formula. The derivative with respect to x of, in particular, for example, x to the pi power, will be pi times x to the pi minus 1. So yes, you take down the exponent, subtract 1 from it, and that is the derivative. Okay? That's when the exponent is a constant. Any constant. Doesn't have to be positive, could be negative. X to the negative 4.5. What is the derivative with respect to x of x to the negative 4.5? It would be minus 4.5 x to the, well, now I have to subtract 1 from minus 4.5. That's going to give me minus 5.5. Okay, so that's all there is to it. Now the bad news about this is that there are many times when you raise something to a power that's not a constant. So for example, we've seen this. What's 2 to the x? That's not the same as x squared, right? Here you've got 2 as a constant, as an exponent. Here x is a variable. And you might also wonder, what would happen if could you do this? Could you take x to the x power? Well, sure. That would mean different things, like 4 to the 4th, 5 to the 5th, pi to the pi, 1,000 to the 1,000. You can talk about that. And the derivative of that is not at all governed by the high school rule. So forget about it. It's only when the exponent is constant that you can take the derivative by bringing the exponent down like that and subtracting 1 from the exponent and doing this. So what happens if you've got 2 to the x, an exponential function? Well, we'll come back to that. I want to do it a little bit later. Let's finish off the easy rules for derivative. What happens if you take the derivative with respect to x of a constant times a function? What would that be? I don't think it would surprise you to know that this is going to be the constant times the derivative of the function. So what this means in English is that constant multipliers, see, c is multiplied by a function. Constant multipliers move in and out of derivatives. So you can take that constant and just pull it out. So for example, what that would mean is that if you knew what the derivative of x to the 5th is, which we do from the high school rule, I can multiply that by 6.08 and say, what's the derivative of that? And the answer is, well, 6.08 is a constant. I can just slide it right out of that derivative operator. So it's sitting out here. And now I just take the derivative of x to the 5th. And we know how to do that. That'll be 5x to the 4th. So constants move in and out. And that's an easy thing to do. Okay? So that tells us that, oh wait, one more rule. What happens if I add two functions together? What if I take this, what if I have two functions, f and g, and I add them together? What kind of a thing do you get? Well, it's no surprise that if you add two functions together, you get a function. So let's give it a name. Let's call it, how about s, not for salary, but for sum, S-U-M. So the sum of two functions, f and g, is another function. What if f and g have derivatives? What would the derivative of s be? What's s prime of x? Well, the definition says it's the limit as h goes to 0 of s of x plus h minus s of x all divided by h. Okay, now we just substitute what is s. This may be a little strange, but S of anything means f of that anything plus g of that anything. So we get f of x plus h plus g of x plus h as s of x plus h. And then you got to subtract the quantity f of s of x, which would mean, let me write it down here, f of x minus g plus g of x. Okay, and all of that is divided by h. Okay, so what's that going to give us? How do we calculate that limit? Well, all you got to do here, it's easier than you think, bring the things together that belong together. Obviously, this f wants to belong together with that f. So I'm going to write f of x plus h, and then let's pull that f of x, which is being subtracted. So I'm going to pull it together like this next to the f of x plus h. Now I can't forget about the g of x, so I'll put that here. G of x plus h, rather. And then there's still that g of x there, and it's got a minus because I have to distribute it. So I'm going to have minus g of x. So that takes care of all the terms from that numerator, and all that's being divided by h. Well, I can split this into two fractions with the common denominator h, and then use the theorem about the limit of a sum is the sum of the limits, so that we end up with this. The limit as h goes to 0 of f of x plus h minus f of x all over h plus the limit as h goes to 0 of g of x plus h minus g of x all over h. So that's because, again, I have a common denominator, I split it into two fractions. And then the limit of a sum of two things is the sum of the limits. That's what I did there. And now I'm home free. You should recognize this guy as the definition of something. It's the definition of the derivative of f at x. But wait, this is also the definition of something. It's obviously the definition of the derivative of g. So what we've proved is that if you have a sum of two functions and you want to take the derivative of the sum, the answer is the derivative of the first guy plus the derivative of the second guy. So in English that says the derivative of a sum is the sum of the derivatives. It shouldn't surprise you to know that the derivative of a difference is going to be the difference of the derivatives. So that's all very nice. Now don't jump to conclusions, because if you multiply functions together, it's not at all going to be easy. And we'll talk about that in the next lecture. But for now, let's summarize what this means if we talk about polynomials. Any polynomial. Polynomials are things that look like this. You know, here's an example of a polynomial. 4x to the fifth minus 7x cubed plus 6.2 x squared minus x plus 15. That's a polynomial. It's an example of what polynomials have. X raised to an integer power, positive integer power, with coefficients and with pluses and minuses separating them. So if you were to take the derivative of a polynomial, these rules that we just talked about, if I want the derivative with respect to x of this mess, the rules that we just talked about say we can take the derivative of a sum and a difference just by taking the derivative of each part. So I take the derivative of the first part, the second part, third part, fourth part, fifth part, add them all up or subtract them as the case may be, and then put them all together, and that's the answer. So what's the derivative of 4x to the fifth? Well, the 4 will pull out. Take the derivative of x to the fifth. That's going to be 5x to the fourth. So 4 times 5 would be 20x to the fourth. Derivative of the second term. That minus 7 is just going to sit there and watch while we take the derivative of x cubed. The derivative of x cubed will be 3x squared. So the 3 times 7 will give you 21. There's a minus there. So minus 21x squared will be that. The next term is going to be plus the derivative of 6.2x squared. The 6.2 is going to come out. We take the derivative of x squared and get 2 times x Then 2 times 6.2 is, I think, 12.4 times x to the first. I don't have to write that. Next, we take the derivative of x, which is x to the 1. So that's going to be 1 times x to the 0, or just 1. Or another way to think of it, x is a diagonal line. So the derivative of that is the slope of that line, which would be 1. Got a minus coming from there. And then the derivative of 15 is the derivative of constant. That would be 0. So plus 0, which I don't have to write at all. Anyway, this is then the derivative of that polynomial. All right. So I think at this point I'm going to pause and load up another video, see how this worked out. We still have to talk about exponential functions, and then I want to do a whole bunch of examples, but this will be a good place to break, and then we'll have a part B to this lecture.